Hi everyone, I am Francine and today I'll be discussing pressure variations of a fluid at rest. So let me first introduce to you what is fluid. A fluid is any substance that can flow and take the shape of its container. It can be liquid like water or gas like air. Unlike solids, fluids don't have a fixed shape, but they can exert pressure on the surfaces they touch. Next, let's talk about pressure. Pressure is the force applied per unit area on the surface. The formula is P equals F over A, where P is pressure, F is force, and A is area. The unit of pressure is the Pascal or Newton per square meter. A simple example, when you dive underwater, the pressure increases as you go deeper because more water pushes down on you. Now, what is fluid pressure? It's the pressure that a fluid, whether liquid or gas, exerts at any point within it and on the walls of its container. In a fluid that's at rest, this pressure acts equally in all directions at the same depth. That's why when you're underwater, the pressure on your ears or body feels the same from all sides. Next, let's define pressure variation. It simply means a change in pressure within a fluid from one point to another. In a fluid at rest, the pressure increases with depth. This is because of the weight of the fluid above. So the deeper you go in water or in air, the greater the pressure becomes. What does fluid at rest mean? When we say a fluid is at rest, it means it's not moving. There's no flow or motion. The only pressure present is static pressure, and it acts equally in all directions at any point. So, no matter which way you measure it, the pressure at that depth is the same. Now, why is this topic important? Understanding how pressure changes in a fluid at rest helps in many real-life applications. In hydraulics, it's used to design brakes, lifts, and water systems. In dams and reservoirs, it helps calculate how much water pressure pushes on the walls and the base. In atmospheric science, it helps us understand how air pressure affects weather and altitude. And in engineering safety, it ensures that structures can handle pressure differences safely and effectively. So, studying this concept isn't just about theory. It is applied in many areas around us. Now that we already understand what fluids are, what pressure means, and why it is important to study pressure variations in a fluid at rest, let's move on to the next part of our topic.
This part will talk about the basic principles of pressure in a fluid at rest. First, pressure acts equally in all directions at a given point in a stationary fluid. This means that at any point inside a still fluid, the pressure pushing up, down, left, and right is the same. This idea is part of Pascal's principle, which explains that pressure in an enclosed fluid is transmitted equally in all directions. This happens because the molecules of a fluid are constantly moving in random directions. When an external force or pressure is applied, the molecules collide with each other, and with the container walls spreading the force evenly, as a result, the pressure at a given point in a fluid acts equally in all planes and in every directions. So in simpler terms, if you push one part of a fluid, that push spreads out equally everywhere inside it. For example, when you are underwater, the water molecules around you are pressing on your body from all directions, up, down, and sideways with equal strength. The second principle states that pressure in a fluid increases with depth because of the weight of the fluid above. In a fluid at rest, every layer of the fluid supports the weight of the layers above it. As you go deeper, there's more fluid on the top, and that extra weight adds more pressure. This is why the deeper you go underwater, the greater the pressure you feel. This relationship between pressure and depth is explained by the hydrostatic principle, which can be expressed using the formula P or pressure is equals to density times gravity times height. From this equation, we can see that the pressure increases as the depth increases or as the density of the fluid increases. For example, if you dive into a swimming pool, you'll notice that your ears feel more pressure the deeper you go. This happens because there's more water above you pressing down. Note that the principles we've discussed apply to both liquids and gases. So both liquids like water and gases like air follow the same pressure principles when they are at rest. This means that pressure in a fluid, whether it's a liquid or a gas, acts equally in all directions and increases with depth due to the weight of the fluid above it. For example, in water, pressure increases the deeper you go underwater because of the weight of the water above you. Similarly, in air, pressure increases as you move closer to the Earth's surface because of the weight of the air above. For example, when you climb the mountain, the air pressure decreases as you go higher. This happens because there are less air above you at a higher altitudes, so the weight of the air pressing down is smaller. These principles of pressure are not just true for liquids, but also for gases under static or at rest conditions. Fluids may behave the same way when it comes to how pressure acts and changes with depth.
Now, let's talk about the mathematical relationship of pressure in a fluid at rest. Pressure in a fluid increases with depth because the fluid above exerts weight on the layers below. Consider a column of fluid with density, height, and cross-sectional area. The weight of the fluid column is W equal to rho GHA. Since pressure is equal to the force divided by area, the pressure caused by this fluid column is P equal to W divided by A, or rho GH. However, the fluid is also under atmospheric pressure at the surface P0. Thus, the total pressure at depth H is P equal to P0 plus rho GH. This equation shows that pressure increases with both depth and fluid density. In the formula, P is equal to P0 plus rho GH. Capital letter P stands for the pressure at a given depth, the total pressure experienced at a specific point within the fluid. P0 stands for the pressure at the surface, typically the atmospheric pressure acting on the fluid surface. Rho stands for the density of the fluid, mass per unit volume or kilogram per meter cube, representing how heavy the fluid is for a given space. G stands for the acceleration due to gravity, approximately 9.8 meter per second squared on Earth. And H stands for the depth below the surface, the vertical distance from the fluid surface to the point of measurement. The term rho GH represents the extra pressure caused by the weight of the fluid above that point. The formula P is equal to P0 plus rho GH shows that fluid pressure increases as depth and density increase. The deeper you go, the more fluid weight pushes down, raising to pressure. Likewise, denser fluids exert greater pressure at the same depth. Therefore, pressure is directly proportional to both depth and density. Now let us consider the sample illustration here. Why jets differ in strength? The top nozzle, or the shallow depth, have less water above it, causing lower pressure, and a shorter jet, while the middle nozzle have more water above, causing a moderate pressure, and a medium jet length. And lastly, the bottom nozzle, or the deepest. It has the greatest water column above, so it has the highest pressure and the longest jet. This demonstrates that pressure increases linearly with depth.
Okay, so now that we know the formula for a pressure in a fluid at rest, let's look at a few examples to see how it works in real life. So let's start off with example number 1, pressure on a diver underwater. A diver is swimming 10 meters below the sea surface. Find the pressure exerted on the diver. So firstly, we need to write off the given data. In this problem, we have a height of 10 meters. Our initial pressure is understood to be 101,325 pascals, which is the normal atmospheric pressure. And then our density is the density of water, which is 1,000 kilogram per cubic meter, and our gravity of 9.8 meters per second squared. Now what we need to do now then is to plug in all those values into our formula of which is P is equal to the initial pressure or the PO plus the density or the rho times the G or the gravity and times the H or the height. So we have here P is equal to 101,325 plus 1,000 times 9.8 times 10, and we will get a value of 199,325 pascals. Example number 2, pressure on a dam wall. The base of a dam is 25 meters deep in fresh water. Find the pressure at the base of the dam. So just like with example number 1, what we need to do here is also just to plug in all those values, and we have the same values for the P initial, the density, and the gravity. The only difference here is that we have a different height, which is equal to 25 meters. So P is equal to 101,325 plus 1,000 times 9.8 times 25. So plugging it in your calculator, we get the value of 346,325 pascals. So to summarize it all, the pressure of a variation of a fluid at rest shows that the pressure increases as depth increases. So this happens because the deeper you go, the more fluid there is above that point, and its weight pushes you down, creating greater pressure. So the relationship is expressed by the formula P is equal to P naught plus a rho g h, which tells us that the pressure depends on the surface pressure, the fluid's density, gravity, and the depth. Understanding this concept is very important in real life. Engineers use it when designing dams and submarines, and even divers need to know it for their safety underwater. So overall, the deeper the point in a fluid at rest, the greater the pressure due to the weight of the fluid above it.